So the second speaker of the morning is Professor Jeffrey Streets from UCI. He will tell us plurally closed flow and a Hull Strominger system.
Okay, yeah, so thanks for that introduction. Thanks to the organizers for inviting me. It's my great pleasure to be here for Tian's 65th birthday conference, and it's my pluriclosed flow in the Hull Strominger system is the title. So let me start by trying to explain to you what is the Hull Strominger system. So this is a system of PDEs that first arose in mathematical physics in these old papers of Hull and Strominger from early 80s, sort of at the very birth of string theory. So fix a compact complex, in their case threefold, with a fixed holomorphic volume form, capital omega. Oh, it broke already. Oh, no, maybe not. You fix a holomorphic vector bundle V and a real parameter alpha. This is somehow the string tension. So the Hull Strominger system uses a Hermitian metric G on that X should be an M. That's on M, and a Hermitian metric on the vector bundle V. Satisfies these three equations. So the first is probably familiar. This is Hermitian-Yang-Mills equation, Hermitian-Einstein equation. This one is probably the least exotic. The second equation is this so-called conformally balanced condition. Yeah, sorry. M is X. Yeah, sorry, that's a typo. Yeah. So it's conformal to a balanced metric. This is equivalent to saying that the holonomy of the Bismuth connection is reduced to SU3. And yeah, so this Bismuth connection will show up a zillion times in the talk. And maybe just for concreteness, this will in general be a connection which is like the Levi-Civita connection of some metric, which has some torsion given by a three-form H. And in the case of a Hermitian metric, this H will always be dc omega. Okay, so this will be the Bismuth connection of a Hermitian metric. And so you're asking that metric connection have reduced holonomy. Now this last equation is sort of the strangest to my eyes. This is sometimes called a Bianchi identity, or in physics literature, anomaly cancellation equation. It's M, yeah. That's a typo. Sorry. Yeah, I'm so sorry. It's M. Sorry, there is no X. I can promise that won't be the only typo. So, but even in the physics literature, somehow going back to the very beginning, there's some ambiguity about what connection you're picking. So what is actually going on in this last term? So I have ddc omega, that's easy enough to understand. But then I have the trace of this sort of representative of the first Pontryagin class of T10 plus V. And so you need the metric on the vector bundle, but you also need sort of an auxiliary connection on T10. Now, somehow, I guess in the original physics discussion, they say, well, it kind of doesn't matter what connection you pick for some physics reasons. And for some PDE reasons that I will never really understand, it for a long time was chosen to be the Chern connection of the metric omega, which makes this kind of a very strangely coupled PDE now, right? So it's some combination of ddc omega and then this quadratic expression in the Chern curvature of little omega. So so maybe I tell a story since it's Tian's birthday. I mean, when we were first starting these Hermitian curvature flow story that I'll kind of get to, at some point Tian asked me to look at Hull Strominger system, and I eventually read Hull's paper well enough to see that this was what they were talking about, and I ran away like my hair was on fire. I mean, I think it looked to me like the craziest thing. I think you'd have to be a maniac to study this PDE somehow. It looked quite unnatural to me, but then in the end I kind of ran in a circle and somehow came back to study this. So in some sense, the point of what I want to say in the talk is to kind of show some kind of minor modifications of this PDE that I think in some sense were probably in some ways known to physicists at the beginning, which gives it a much more kind of natural setting, I would say. Something that looks much more natural to a geometer. Okay, so in particular, well, there's, yeah, so if you look hard enough at the original physics works, they suggest that you should not use the Chern connection of the metric omega on the bundle T10, but you should fix like an auxiliary Hermitian-Einstein connection on T10. Okay? So it should be decoupled from the metric on the base. Okay? Okay, but so let me I want to relax this system in a couple ways. So in particular, in principle, in this anomaly cancellation, what you're seeing is a representative of the first Pontryagin class of this bundle, of T10 plus V. But I'm just going to replace that by an arbitrary holomorphic vector bundle V. Okay, it'll just be an arbitrary vector bundle V. And I don't want to necessarily assume the existence of a holomorphic volume form. So I'm going to replace this conformally balanced condition just by sort of its geometric consequence, which is the vanishing of the Bismuth-Ricci form. And with these choices, you arrive at this so-called coupled Hermitian-Einstein system. Okay, so this was terminology created by my collaborators, who I failed to mention, Mario Garcia-Fernandez and Raul Gonzalez-Molina. So we have this kind of relaxed Hull Strominger system. So we have still Hermitian-Einstein. We have special holonomy for the Bismuth connection. And then now this is this Bianchi identity or anomaly cancellation. Okay. And yeah, here we're thinking of V as this holomorphic vector bundle, which is the adjoint of some complexified principal bundle, principal K bundle. And so you need an inner product on the Lie algebra to sort of define this term. And so to recover the anomaly cancellation equation in the form on the previous slide, crucially, you have to pick an inner product of mixed signature on the bundle. So basically, this equation contains the previous one as a special case. If the bundle is split, as it is here, like T10 plus V, and then you pick an inner product, which is sort of positive definite on one factor and negative definite on another. Okay? Then you'll get this anomaly cancellation. So I mean, I'm just trying to emphasize this difference in sign, this minus sign in the middle. Okay? So you have mixed signature inner product on the Lie algebra. Okay? This is a key point for later. Okay. But so still, I think that system probably looks somewhat obscure. At least to me, it still looks a bit obscure and strange. So the point is, the kind of starting point for what I want to say is that you can properly understand it through a symmetry reduction. Okay? So here's this basic proposition. So I sort of strip away the complex geometry, and I just want to understand what the sort of equations of motions are, or supergravity equations kind of induced by this PDE. Okay, and here we have it. So you have the following system of three PDEs. So here H is this minus DC omega, A is the Chern connection associated to H, and this theta is the so-called Lie form. So you take D star omega, that's a one form, which of course vanishes in the Kähler case, and apply J. So we call the Lie form, okay? So if I just suppress all the terms involving the Lie form, this one, D theta, I theta sharp H, if I just suppress all of those, what do we really see? So you have this kind of coupled Einstein equation. So you have Ricci is not 0, but it's given by some quadratic expression in H and F. And then the H is, well, a co-closed. And then you have this Yang-Mills type condition. Of course, we already know we have this Hermitian-Yang-Mills PDE for the connection. And so together with this anomaly cancellation equation, this becomes some nice elliptic system. Okay? So the H is no longer closed, but you prescribe DH in terms of this quadratic expression in F. And so it becomes an elliptic system. Yeah, and then so the key point is that this system, again, sort of stripping away the complex geometry, can be understood as the vanishing of the Bismuth-Ricci tensor for certain data on the principal bundle. So you can genuinely understand this as a kind of modified Ricci flat equation on P. And here again, yeah, when I say Bismuth connection, I mean some connection like this, but the H will no longer just be DC omega. So in particular, the metric on P, of course, is what you expect. It's the usual sort of Kaluza-Klein reduction. You have a metric on the base, you have a principal connection, and an inner product on the Lie algebra. You can use this to define an invariant metric on the total space of the bundle. So this is the usual construction. But the H is slightly non-obvious. So the H on the total space, you pull back the torsion form to the total space, and then you have to modify by the Chern-Simons 3 form associated to the connection. Okay? Yeah? this is like a PDE for, well, I guess if I'm kind of ignoring the complex geometry, it would be like G, H, and A, but really just sort of G and A. Or little g and little h even, the metric which induces the Chern connection. But yeah, so this is the correct form of the 3 form on P, and you can sort of see its exterior derivative is exactly this anomaly cancellation quantity. This is kind of the point, is that this funny anomaly cancellation equation is really just asking that this natural 3 form built out of the torsion of the metric on the base and the Chern-Simons form of the connection is closed. That's it. Okay, that's it. So this is really somehow what this anomaly cancellation equation should be thought of, I would say. But okay, so given that we can think maybe of this Hull Strominger system modified slightly as the vanishing of the Bismuth-Ricci tensor, well, we have this tool that we've developed for trying to construct data with vanishing Bismuth-Ricci tensor we call a generalized Ricci flow. And in the complex geometry world, this is what I introduced with Tian, this so-called pluriclosed flow. Okay, so let me just sort of very briefly, there's no clock in the room, very briefly recall what is going on with these. Okay, so generalized Ricci flow is a PDE for a Riemannian metric in a 2 form B, which looks like this. So the metric is evolving by Ricci flow plus this 1/2 h squared. This is the natural contraction of H with itself to form a symmetric 2 tensor. And then the B field is evolving by minus D star H. And I guess I didn't write it, but H will be some background H plus DB. Okay? So equivalently, this is just saying that G minus B is evolving by the Bismuth-Ricci tensor. So the Ricci tensor of a connection with skew torsion, like over here, has a symmetric and a skew part. And in any case, it fits together like this. Okay, so but there's no complex geometry around. So on the other hand, we can study this pluriclosed flow. So this is what I introduced with Tian. So if I have a family of pluriclosed metrics and 2002 forms, we say it's a solution of pluriclosed flow if the metric is evolving by minus the 1,1 piece of the Bismuth-Ricci form. So this is the natural representative of C1 associated to the Bismuth connection. And then beta is evolving by the 2,0 part. And then, so similarly, you can say that omega plus IB is just evolving by the full Bismuth-Ricci form, which is not 1,1. Like there is a 1,1 and 2,0, 0,2 part. Okay. And then the result I showed with Tian sort of at the beginning of this is that solutions of pluriclosed flow are gauge equivalent to solutions of generalized Ricci flow. Okay. And importantly, the sort of culprit in the gauge fixing aspect of the story is always this Lie vector field. You study this PDE, and then you have this 1 parameter family of Lie vector fields that generate some diffeomorphisms, which when you pull back gives you the generalized Ricci flow. Okay. Okay. So right, but so this a priori is not related yet. So let me go back to the setting of the Hull Strominger system. Okay. So I'm going to call a 1 parameter family now of Hermitian metrics, omega on the base, and Hermitian metrics on this auxiliary vector bundle, a solution of quote unquote pluriclosed flow. I'll explain in a second. If we have the following system of PDEs. So omega is evolving by what we expect from pluriclosed flow, this 1,1 part of the Bismuth-Ricci form, and then minus some special quadratic expression in terms of the Yang-Mills curvature. And then the metric H is evolving by Hermitian Yang-Mills flow. This is exactly sort of the like Donaldson flow in Hermitian Yang-Mills theory, except of course this omega is the flowing omega, right? So it's not literally Donaldson flow, but it's sort of coupled to this Ricci flow, you could say. Okay. Okay. So what is going on with this system? Okay. Why do I introduce it? So okay, one thing, it's strictly parabolic, so it has a nice basic regularity theory. Fine. Well, yeah, it really sort of okay. And it might not be completely obvious at the outset, but the fixed points do solve this coupled Hermitian-Einstein system. So it is a parabolic flow for solving for this slightly relaxed version of Hull Strominger. And it preserves the anomaly cancellation equation, right? So the sort of most basic aspect of this pluriclosed flow equation, which I didn't really say, is that you ask that your initial three form be closed. That's the pluriclosed condition, and that's of course preserved by the PDE. But as we saw, that condition in this dimension reduction picture is basically the same as this anomaly cancellation equation, okay? So for this equation, the anomaly cancellation is preserved, okay? And then using this sort of dimension reduction ansatz that I described, you can prove that this flow is gauge equivalent to generalized Ricci flow on the principal bundle, on P. So it literally is generalized Ricci flow on P. But now here's the sort of crucial point. What I write here is true, even though, depending on the signature that you pick for this inner product, the metric on P might not be Riemannian, right? So basically, the signature of the metric on the fibers is dictated by the signature of the metric on the Lie algebra. And of course, it doesn't really cause a problem with the parabolicity because everything's invariant in the vertical directions anyways. It's sort of a nice parabolic system regardless of this signature. But for instance, now for this generalized Ricci flow, we kind of have a host of monotone quantities. There's a Perelman monotonicity. There's a scalar curvature monotonicity. There's all manner of nice kind of monotone quantities that we have for generalized Ricci flow, which of course will all fail if this metric is not positive definite. It will affect all of those monotonicity formulas. So that they will all kind of blow up in your face if you do impose this mixed signature inner product on the Lie algebra the way the physicists like, okay? So part of the sales pitch for the talk is I will sort of heavily advocate for picking this thing to be positive definite. Because immediately you get a PDE with many nice quantities associated to it. And moreover, for instance, like the fixed points are amenable to this like regularity theory developed with Aaron and Shin-Fu. So it's sort of a much nicer PDE when you asked that this be positive definite. And then, yeah, so in the very simple cases where the structure group is, say, an even dimensional torus, you can show that this is gauge equivalent to a K-invariant pluriclosed flow on the total space of P. This is why I kind of put just pluriclosed flow in quotes, that in some sense it is literally a symmetry reduction of pluriclosed flow on a principal bundle. This is more or less true in general, but there are some caveats. Like it's basically true, but you don't get a nice sort of description into invariant pieces in the case the structure group is non-abelian. But anyways, that's maybe not so important. Okay, so we have this PDE now in principle for understanding solutions of Hull Strominger. I want to show you a nice a priori estimate, even for the original Hull Strominger system, that comes out of this picture, or really comes out of a kind of different formulation. So I'm going to describe a reformulation of this flow in terms of the geometry of what is called a holomorphic string algebroid, which I'm sure no one in this room knows what it is, most likely. So this builds on a number of really nice precursor results in physics literature. There's this nice paper of De La Osa, Larfors, and Svanes, and then recent work of my collaborators. So if you fix some background data which satisfies the anomaly cancellation equation, okay, I can define this special holomorphic bundle. So I take the holomorphic tangent bundle and direct sum V and direct sum the holomorphic cotangent bundle. We call that Q. And then I can define a Dolbeault operator on this. Now, I write this formula down. It's probably somewhat blinding. So this is some D bar operator, which depends on the metric data, right? So the D bar operator depends on the initial choice of Hermitian metric on the base and connection A. And it looks like this kind of somewhat jumbled mess, but it's sort of incorporating the D bar, obviously the D bar operators on these separate bundles. And then you can see some of these extra terms. I should say this also, in a sense, is generalizing earlier work of myself, Mario, and my student Josh Jordan, who's here, where in that case, the principal bundle is turned off. There's no V. And you can sort of see just from these first three terms are all you would get. A d bar of the vector piece, d bar of the covector piece, and then this extra term, the interior product of V into del omega naught. You can sort of see from that term that the d bar, the fact that this is a d bar operator, that it squares to 0, is exactly the condition that omega naught is pluriclosed, right? You exactly need that d bar of this 2-1 form is 0 to get this. And then so somehow, okay, with these extra gauge terms, the integrability, the fact that this d bar squares to 0 is exactly equivalent to this anomaly cancellation, okay? So the anomaly cancellation equation gives you a d bar operator on this funny holomorphic vector bundle. Okay, but so what is the point? So here's the theorem. So I fix this omega t ht, a solution of pluriclosed flow, and then you have to further couple to a flow of 2 zero forms beta. So I completely suppress this part, but anyways, it's completely explicit. Then this data, omega, beta, and h, determines a family of Hermitian metrics on this bundle Q. And somewhat amazingly, that family, so again, it's completely explicit, although in a sense, highly non-obvious if you're not familiar with kind of the geometry of these string algebroids. But anyways, it's a completely explicit formula to determine the one parameter family of Hermitian metrics G on this bundle, which again satisfies this sort of coupled Donaldson type flow. So it's exactly, again, exactly Hermitian Yang-Mills flow, except, of course, the metric you're taking the trace with is also flow. Right? So kind of miraculously, you can interpret this as this sort of Donaldson type flow. Okay. And then so this has a really nice consequence, which is more or less immediate once you have this picture, which is a generalization of Yao's C3 estimate, okay, for the complex Monge pair. So, and again, here I'm going to emphasize that I'm picking the Lie algebra to be definite. Okay, I'm going to impose this assumption. So, given two Hermitian metrics on this vector bundle, this string algebroid, I'll let epsilon denote the difference of their Chern connections. And then this phi quantity is just some sort of scale invariant CK+1 norm, okay, of the metric G. You just take the Chern connection and its derivatives scaled appropriately, okay, some scale invariant CK norm. So the theorem is that if you have a solution to this pluriclosed flow and you have a uniform ellipticity condition, which in this case is phrased in terms of the generalized metrics. So if these generalized metrics are uniformly equivalent to some fixed one, then you get smoothing of all the higher order derivatives, okay? Okay, and actually, yeah, I've been emphasizing so much this definite case. We can actually sort of prove, well, we can prove a closely related result for arbitrary pairing. You can basically prove the same estimate using some related ideas, but I just skipped that part. So yeah, maybe the proof, again, is sort of not that surprising to anyone who's ever seen Yao's C3 estimate. So it's a fairly straightforward calculation. You just compute the evolution of the difference of Chern connections along the flow, and you get this kind of simple kind of Bachner formula cancellation of the highest order terms, and it basically reduces to essentially like a linear looking PDE, which is sort of the miracle of Yao's C3 estimate, right? So the same thing happens here again for this funny generalized metric, okay? But here, yeah, for this proof, again, you can kind of see I have this one extra term. So I apply the heat operator to the norm squared of the connection. I get some nice negative terms like you would expect, but then there is one sort of nonlinear term, this inner product of f squared with epsilon squared, which again, that will have a sign precisely when this inner product is definite. It's chosen to be definite, okay? Okay, but so anyways, it's essentially a trivial maximum principle to get the estimate for epsilon out of these equations, and then it's just Schauder estimates really to get the rest of the regularity, okay? Okay, So yeah, we also can prove a global existence result. So if I fix as my background a bismuth flat manifold. So for instance, here in like the context of like the sort of usual, like in the Hull Strominger system, they're very concerned with dimension 6. So like here, for instance, you could take like Calabi-Ekman, like S3 times S3 as a bismuth flat metric. And then I'm going to pick a flat holomorphic vector bundle. So I sort of turn the vector bundle off, more or less. This determines a holomorphic string algebroid. And then I can just take any initial data on that. So I take any initial data for the flow, which determines some metric on this algebroid. Then we prove the solution is global. The solution to the PD exists for all time. And it will converge to a metric which, again, is determined by a bismuth flat metric on the base and a flat metric on V. So it sort of completely describes this PDE on these backgrounds. Okay, it's a very special background, but it's a complete answer. Okay, and yeah, and again, the proof with this string algebroid picture around is very, very easy. It's very easy. So the assumptions of the theorem basically tell you that you have a background metric on E, which is Chern flat. Okay, so you can just revisit these evolution equations in this Yao C3 estimate, and they just become like sharp. There's no like background terms, and for instance, you apply the heat operator to this trace, and it has a sign. This trace actually governs both an upper and lower bound for the generalized metric, which is a slightly non-obvious point. But anyways, and then you immediately get an a priori decay estimate even for the Chern connection. Okay. Yeah. Okay. So yeah, let me just end by making some highly speculative remarks. So for many decades now, Yao and various collaborators have proposed using this Hull Strominger system to address this so-called Reed's fallacy. So this Reed's fallacy is this famous old paper that suggests that the space of all complex threefolds with holomorphically trivial canonical bundle should be connected in some sense, which requires this passing through these conifold transitions. Okay? And even Reed himself in the original paper kind of suggests that, well, you need some geometry around, you need some kind of equation around to try to sort of geometrize the transition. Okay? And Yao proposed using this Hull Strominger system for this. But yeah, so I'm trying to kind of emphasize a slightly different approach to this system, which maybe suggests a slightly different approach to Reed's fantasy. So we have genuinely modified it from the physical setting to ask that this Lie algebra inner product be definite, which gives, like I said, a number of really nice analytic estimates. And so we can ask, well, can it be used to geometrize Reed's fantasy? So here you run up against what, as I understand it, is more or less the reason why they chose this mixed signature inner product in the first place. So you can prove a no-go theorem that says over a complex threefold with holomorphically trivial canonical bundle, the only solutions to this coupled Hermitian-Einstein system have a trivial Yang-Mills piece, and the base manifold has to be Kähler-Calabi-Yau. So these are the only possible sort of genuine solutions relevant to Reed's fantasy. So this already, okay, tells you something more subtle has to happen for the flow on these backgrounds, on backgrounds other than these. By some formal considerations, you sort of expect that this flow I defined should be global if the canonical bundle is trivial. So somehow the behavior at infinity should reflect some maybe collapsing geometry of the base, which should be maybe dictated by the choice of bundle. And you can see that this happens in some very sort of elementary solutions, that you can kind of get different cycles to collapse depending on what bundle you put over your manifold. Yeah, and so maybe I just end with a couple questions. So I didn't emphasize this so much, but the other sort of aspect of the Yao school approach is that they tend to initially solve for this conformally balanced metric And then they want to modify the conformally balanced metric to solve the anomaly cancellation equation. In a sense, our approach is inverted. We ask a priori for a solution to the anomaly cancellation equation. This is preserved along the flow, and we try to find this, not necessarily conformally balanced, but this special Bismuth-Holonomy metric. Okay? So we've kind of inverted the order of solving the PDEs, you could say. And so, well, given that, an interesting question is sort of what, given, say, a complex threefold with homomorphically trivial canonical bundle, which bundles admit solutions to this anomaly cancellation equation, this Bianchi identity. And of course here, just for emphasis, I mean independent of any other PDE. I just want to solve the anomaly cancellation equation. Yeah, and then also which bundles should we pick? So if we have this idea that one Calabi-Yau should sort of encounter a conifold transition to connect to another Calabi-Yau, what bundle should we pick to sort of produce that singularity? I think is an interesting question. So, okay, yeah, thank you.
Any questions? Okay, any question from Zoom?
Oh, maybe Yanir.
Jeff, so very nice. So I guess this so you have if you have a initial metric which satisfies this anomaly constellation equation, then the flow preserve this condition,
Yeah,
right?
that's right.
So,
yeah.
so then I guess your question is, so the issue, and I guess there's a related question, which is somehow related to your question here, is to giving a two vector bundles. Suppose they have a second same chunk character, same second chunk character. Of course, you can always write as a D exact form, D of some two forms. Maybe DDC, I don't know. And so the point is whether you can, I guess your question is whether you can make that omega to be positive, right?
Exactly. Yeah, that's exactly the point. Yeah. And so, like, for instance, on a Kähler background, the problem is purely topological.
Yes, there's some, yeah. But for conifold transitions, maybe that's the construction is very explicit, right? I guess even Lupon and I did some construction. So maybe then one can construct a metric there. I mean, in that particular case, maybe one can say such
a singular space. Is that what you mean?
The single space, then you smoothing, right? You can write this fantasies. You do a blow down from the Calabi-Yau threefold, and then blow down some rational curve. So then do a smoothing. So, so on the singular one, maybe you have. I mean, you can start with a singular one, then try to see how smoothing preserve that things, because smoothing is rather explicit too. You can actually write down the. I wrote a short note because this smoothing you can really write down infinitesimal deformation form. So maybe that's possible to do that case.
Okay. Yeah. Well, maybe you can send me the note. I don't know that paper. Yeah. Yeah, there's been a lot of recent work about sort of passing various geometric constructions through these.
So this, what I wrote was a long time ago. It's algebraic Ziff run. They use algebraic called T1 lifting to prove smoothing is possible. So what I did was I can actually write down the differential forms to prove that.
I see. Okay.
In the 90s, actually, paper.
So you call this no-go because you really want to get to the non-Kähler Calabi-Yau ones from the other ones?
No, it's this kind of physics terminology. It's like there's no, in their eyes, it would be like no non-trivial solutions. That's why they would call it no-go theorem. But
Right, but you want to sort of see how you to go from all of them, and this would only sort of restrict you to those
Yeah,
Calabi-Yau ones.
right, exactly. Yeah. Well, yeah, and that's right. Yeah. I mean, and yeah, it's sort of a conceptually different approach. Like as I understand it, like the idea traditionally is maybe if you're lucky for the right bundle, you can solve this full Hull Strominger system maybe in every Kähler class, and then you let the Kähler class degenerate in the right way, and you'll see this conifold transition, and then you can pass the Hull Strominger system through the conifold transition to the other side, right? But here we're sort of suggesting that maybe the kind of singular limit is constructed directly at time infinity of some flow, right? So even a Kähler Calabi-Yau, I pick a non-trivial bundle intelligently chosen in a way I don't know. And then maybe at infinity, I see a singular limit, which is like which has a particular contraction of rational curves and satisfies some singular Hull Strominger equation that I can push to the other side, maybe. This is all pure speculation.
And also, I was wondering, Reid, was he interested in this sort of as linear, I mean, anti-canonical series of some underlying fourfold Fano or something, or?
I don't know.
No?
I don't know. I thought it was just sort of pure three-dimensional sort of algebraic geometry he was interested in, and realized that it couldn't all be algebraic, and
Right. Okay. And my last question is,
this idea.
there's this paper of Lanave where they kind of show that the Ricci flow, Kähler-Ricci flow can be understood as like on an equation on a line bundle, one dimension higher. They convert this parabolic equation into like a degenerate elliptic equation on the total space of the line bundle. Is that something that
I never thought about that,
Yeah.
but yeah, that's interesting. I never thought about that, but yeah, that's interesting.
It can be written as a kind of solid on the space, on a space one-dimensional higher. Yeah. Maybe it's possible to do that too here.
Any other questions?
So also you said somewhere, I just try to understand better or make clear. So you say the Bismuth-Ricci flat will imply this equation, right? Will imply a Strominger system.
I kind of, when I discuss this dimension reduction, right now I kind of remove the complex geometry. I mean, I guess what I'm saying is the coupled Hermitian Einstein induces this PDE. I mean, yeah, I'm being a little bit vague, and I even kind of ignore these gauge terms. So all the terms involving the Lie form, in a sense, are gauge terms. This is sort of like a soliton type equation. And all I'm saying is, if you ignore those gauge terms and then you impose this ansatz, sort of, I didn't write down the metric, but just the usual Kaluza-Klein metric on P, together with this H, it's Bismuth-Ricci flat.
So the up to gauge transformation is a Bismuth-Ricci flat.
Yeah, and more generally, it's like a Bismuth-Ricci soliton. Yeah, that's right.
Thank you.
I have a question. Could you expand a little more on how this Hull Strominger system could be used to address Reid's fantasy? I mean, you start with some Calabi-Yau threefold, and you want to see that you can, or you have two Calabi-Yau threefold. You want to see you can connect them with conifold transitions. Where would the bundle come from to start with?
Well, that's I think part of the question. Of course, you expect the Calabi. I mean, you expect this kind of web in Reid's fantasy to be connected. It's not like it's a line. So somehow it's connected in some very complicated way. And so you imagine. I mean, this is all still sort of work in progress. And with my collaborators, we're trying to at least sort of formally solve the problem of what bundle should you pick to sort of dial in the correct conifold singularity at infinity. It's not so clear if there even is kind of like a formal way to do that, in the sense that, like for instance, in the Kähler-Ricci flow theory, you can kind of formally predict singularities just based on the structure of the Kähler cone. Like there may be something like that going on with this, where you can kind of formally predict a particular conifold singularity at infinity by picking a particular initial bundle. So the idea is you aim at that conifold transition, you somehow know which bundle to pick, you hope you can solve the anomaly cancellation equation on that bundle, you start the flow, and then you see that singularity at infinity. It's like 6 extremely difficult conjectures put together.
Jeff, for if you start with this Calabi-Yau, that bundle is trivial, right? It's just a tangent bundle, and yeah. So
Well, no,
the
I guess what I'm saying is,
question can be what the Bern concerned is the question can be made algebraically or complex analytically. So you want to find the right. So original this conifold transition has nothing to do with vector bundles. So now you want to add the actual structure to see what is a vector bundle associated to it.
well,
I
that's
mean, for
true.
Calabi-Yau, you can start with Calabi-Yau, that's trivial. And you have a trivial initial bundle. So through a conifold transition, so what kind of bundle you want to? It's not. I think this can be made into a complex analytical question, or at least algebraic. I mean, possibly algebraic geometrical question here.
Well, yeah, I mean, that would be great. I guess I was, yeah, maybe
I mean, there's
approaching
some positivity condition. That might be difficulty, but otherwise, probably it's just about the same chain character. Only thing is you want this transition. Better this is like both chain classes, I think. So you want both chain classes in the secondary both chain classes to be positive, to can be represented by positive
Yes.
form. That's might be a difficulty to do,
Yes.
right? I mean, this omega now is just become both chain classes in a sense.
Yes, that's right. I mean, maybe just one comment I make, like even like a very, very simple example, like on tori, of course it's scalar everything, but depending on what bundle you pick, you will see different blowdown limits at infinity. You sort of contract different cycles which are determined by the topology of the bundle you pick. So I mean, there is some very, very elementary precursor for the idea that the topology of the bundle can influence the nature of the singular limits at infinity. I mean, like I said, it's only like toy examples, but but yeah, it's slightly unclear even formally, like from the PDE. Even if you kind of know the right conifold singularity you want to produce, what bundle you should pick.
Any other questions? So then let's thank Jeffrey.